So enthalpy changes are something that is going to accompany any sort of chemical reaction and for some physical changes, specifically those involving the dissolving of salts. We do not always have energy changes that are going to result with something warmer being added to something cooler. When a chemical reaction occurs, energy is released in the process of forming bonds, and energy is consumed in the process of breaking bonds. With a salt dissolving, remember we talked about that there were energy changes associated with the solvent expanding and the solute expanding, and that energy was released when the two were able to interact with one another. And depending on which of those processes resulted in a greater energy change, you could have both endothermic salts where energy had to be absorbed to allow the salt to be able to dissolve in water, and you could have exothermic salts where energy is released. And since energy is basically the equivalent of enthalpy in a constant volume environment, those two can be used interchangeably with one another. We will see that with enthalpy, we tend to be a little more generic with representing the heat changes because it tends to be regarding an amount of a substance, while Q is for just a specific amount of a given substance. So Q is for one point in time, while enthalpy could be used for a variety of amounts for a given substance. When we're dealing with standard enthalpies, we see that degree sign after the delta H, and that's telling us the most stable form we would find that substance in at a pressure of 1 atmosphere and at 25 degrees Celsius. For the majority of our substances, they're going to be your pure substances. We're going to find them in either solid, liquid, or gas forms. For aqueous solutions, they will have concentrations of 1 molar. Sorry. So when we are looking at enthalpy, you will typically see it written as kilojoules or joules, or you could see it as kilojoules per moles of reaction. And the reason you won't see it per mole just overall is that it's based on the chemical substances and their stoichiometric ratios from their balanced equation. Delta H is going to be proportional, that enthalpy value, for those different reactants and products and their relative amounts that are present. Depending on how much of the reactants and products we actually are consuming or forming, we can determine what the energy amount would be associated for that specific amount of a reactant or product. So we can use delta H to calculate Q for the amounts of reactants and products that we have in our change. So here we have 1 mole of methanol is burned at constant pressure, and that 750 joules of energy are released as heat. So we want to calculate delta H when 24 grams of methanol is being burned. So we have what the energy amount is per 1 mole. That 750 joules of energy are released for every 1 mole. And we have the chemical formula for methanol, CH3OH. So we can take that 24 grams and convert it into moles using its molar mass, which would give me 0.749 moles. So I have roughly 3/4 of a mole of methanol. Well, if 1 mole of methanol would generate 750 joules, 3/4 of a mole of methanol would be able to generate a little less energy. So I would take the amount of moles that I have for my methanol, and I would set up a relationship between the amount of energy I know is released for every 1 mole of methanol. And you could have done this for grams as well. You just would have had to take the 750 joules and divide it by the equivalent 32.05 grams that is equal to 1 mole of methanol. But when I go ahead and multiply and divide, I see that this gives me 562 joules of energy. And it would have been better suited if I had said Q for this, so I apologize for using delta H as my unit. and this should actually have 2 sig figs because of the 750 joules. So the more significant figures response would have been 560 joules. So if I was going to take my balanced equation for methanol, and if I went through and balanced it to show it undergoing combustion, you will see that I have 2 moles of methanol for 3 moles of oxygen, and they combine together to make 2 moles of CO2 and 4 moles of water. And the delta H for this specific reaction is 1500 joules. It's negative because it's releasing heat. So 1500 joules of energy would be released for every 2 moles of methanol, and that's how that 750 joules is coming out. I could do the same thing proportionally for oxygen, but it would be per 3 moles of oxygen, for 2 moles of CO2 being made, and for 4 moles of water being made. So this information about being able to relate Q to delta H is going to help us when we're solving calorimetry problems. And calorimetry problems can involve both physical and chemical processes. When you are at constant pressure, we're typically dealing with coffee cup calorimeters, and we can use those to evaluate the change in temperature in our surroundings and be able to use that to find out things about our system, whether it be a chemical reaction or a dissolution process. When you are dealing with constant volume, we tend to be dealing with bomb calorimeters, where we are combusting some sort of fuel source and determine the energy requirement associated with that. In this particular situation, the surroundings is actually just going to be the calorimeter, specifically the bomb calorimeter, and we're going to see that that gets calculated a little bit differently than the energy changes we would see with a constant pressure calorimeter, but it's actually, I think, going to be a little simpler for you. Sorry about that. So this is an example of a bomb calorimeter. Again, you've got the reactants in your container. You can measure the temperature outside. It's a constant volume because that is the shape, that object that in which it's been placed. And so when this gets ignited, all of the energy is going to get transferred to the calorimeter. And so that is able to act as our surroundings in this particular calorimetry situation. So in the first example I'm going to deal with you, it's a chemical change. We have hydrochloric acid and barium hydroxide combining to make barium chloride and water. And we see that delta H for this particular reaction is 118 kilojoules that's being released. We're first going to calculate the heat that is going to be generated when 100 mils of 0.5 molar HCl is mixed with 300 mils of 0.5 molar barium hydroxide. So I'm going to come back to the rest of that shortly, but we're going to focus first on the amount of heat that we need to, how amount of heat that's released when this particular amount of hydrochloric acid is mixed with this amount of barium hydroxide. We just got done doing stoichiometry problems, and we know that if you have different amounts of your reactants, that can influence how much of your product can be generated. And that's also going to have a proportional effect on the enthalpy change for your chemical reaction. So since we have a volume and a molarity of our reactants, we're going to find the moles of both of those reactants. Again, I'm going to come back to this part here in a second. So which one is limiting? I'm going to find my moles of HCl, taking the volume in liters and multiplying it by its molarity, 0.0500 moles for HCl. And I'm going to do the same thing for barium hydroxide, 0.150 moles. And it doesn't matter which product I go to, I'm just trying to figure out which reactant is limiting. And so I chose to go to water in this scenario. 2 moles of hydrochloric acid would result in forming 2 moles of water. So I would have 0.05 moles of water that are generated from the 0.05 moles of HCl. And if I did the same thing with barium hydroxide, the ratio would be a little bit different because I only need 1 mole of barium hydroxide to react with the 2 moles of water. And so I actually am able to make more moles of water from my barium hydroxide. So my limiting reactant is my hydrochloric acid. Why that's important is that that's going to help us determine how much heat is given off in this reaction. If we assume all of the hydrochloric acid was consumed, and we know what the enthalpy change was for our reaction, negative 118 kilojoules, we know that much heat was released for every 2 moles of hydrochloric acid that were consumed, because the coefficient for HCl is 2. So if I have my moles of hydrochloric acid, I can relate that to my enthalpy change for HCl, that 118 kilojoules was released for 2 moles of hydrochloric acid. And that helps me see that actually 2.95 kilojoules of energy was released based on the amounts of reactants that I had present. Now I'm going to go back for a second. So we're going to hold on to that 2.95 kilojoules. And if we read the rest of the question, it says you can assume that the temperatures of both solutions started at 25 degrees and that the final mixture has a mass of 400 grams and a specific heat of 4.18. Let's calculate the final temperature of our mixture. Any temperatures you're measuring in calorimetry problems are going to be dealing with the surroundings. The reactants that are present are your system, and the solution in which that reaction takes place is part of your surroundings. We can always relate the Q of our system to the Q of our surroundings, because conservation of energy tells us that the amount of heat that is absorbed or released by the system is equal in quantity to the amount of heat released or absorbed by the surroundings. Because one is undergoing an exothermic change and the other is going through an endothermic change, we have to switch the sign. But now that we have the Q for our reaction, which we just calculated, we are able to find the Q of our mixture. And when we are dealing with the surroundings, when we're dealing with temperature changes, we can use MCP delta T to relate the Q of our mixture to its temperature. You have in this problem the mass of your mixture, you also have the specific heat of your mixture, and you know the initial temperature of your mixture. So if you know all of those pieces, and now that we know the amount of heat that was released by the reaction for our limiting reactant, the 2.95 kilojoules, we know that that is the amount of heat that the surroundings, the mixture, had to absorb, as long as I change the sign. So the Q of the reaction is the same as the Q of my mixture, but it's just opposite it in sign. So I know now that my mixture's Q is 2.95 kilojoules, but because my specific heat was in joules, I'm going to need to convert that into joules as well. One of them's got to get converted. It doesn't matter which. But I can't have a different unit in my CP for joules than I have for my Q. And so I know that my energy change, 2950 joules, that's how much heat the mixture absorbed from this reaction, was determined using the 400 grams of the mixture, the specific heat of my mixture, and my initial temperature. At this point, you should be able to hopefully recognize that some units are going to cancel out, and you can algebraically solve this through, or you can use your calculator. So the joules and the grams cancel. And if you go through and combine the like terms together, multiplying 400 by 4.18 and dividing that into 2950, you get that there was a temperature change of 1.76 degrees Celsius. If we started at 25 degrees and we want to know what our final temperature was, we're going to see that the final temperature increased slightly from 25 to 26.8. So again, your system will always be able to relate to your surroundings in terms of your Q. Delta H values are going to be specific for the change occurring within your system, and we have to be able to relate those to the specific amount of reactants that are actually consumed. And in terms of your mixture with a constant pressure calorimeter, you can relate that using MCP delta T. If you have a bomb calorimeter, mass is not going to be needed to calculate the amount of heat that is released or absorbed by the bomb calorimeter. The bomb calorimeter is just going to have its energy change determined using the heat capacity of the calorimeter and the temperature change that took place within that bomb calorimeter. So here we have 0.1964 grams of quinone was burned in a bomb calorimeter that had a heat capacity of 1.56 kilojoules for every degree Celsius. We're told the temperature of the calorimeter increased by 3.2 degrees Celsius, and we want to calculate the energy of combustion of quinone per gram and per mole. So the combustion energy is that enthalpy change, delta H, so we want to find the Q for our reaction. We have information that would help us find the Q for the calorimeter. We have its heat capacity and we have its temperature change. So when we multiply those two together, we are able to get the amount of heat that was absorbed when the quinone was combusted, 5 kilojoules. That tells us that 5 kilojoules of heat was released when the quinone went through combustion. And so now that I know what that Q value is for my specific amount of quinone, I can calculate what delta H is per gram by dividing that Q of the quinone by the mass of quinone that I had present. That's how much energy was released for the specific amount of quinone. So if I want to find delta H, I would divide those two to get it into kilojoules per gram. And then I could also get it into kilojoules per mole by taking the grams and converting them to moles, or by using my molar mass to convert the delta H for kilojoules per gram to kilojoules per mole.